Our today's speaker is Mariia Savchenko from Institute of Applied Mathematics and Mechanics with the talk Harnack inequality and continuity of solutions for non-uniform elliptic equations with non-standard growth. And as I said last time, despite of the main topics of our seminars, which are mostly probabilistic, moreover, belongs to the random process theory, stochastic analysis, such fields, maybe most of participants use parabolic or elliptic equations when working with diffusion processes and solving some probabilistic problems. From this point of view, I think that for us will be very useful to see the modern achievements in this field. From this point of view, I asked Mariia to present some of her results with courses at our center. Please, Mariia.
Thank you for the introduction. So I would like to present results which were obtained in joint work with Igor Skrytnik, Alexander Hadji, and Mikhail Vaitovich, who met last spring in Mariupol, and I'll present his last scientific results. So let's start. We will consider second-order elliptic equations in divergent form. Under divergent, we can see here non-standard expression. But for such type equations, this expression is usual because all qualification estimates and conditions formulate in terms of the function g. And if we have here function g which depends from the x and nabla u, so we need to work with Orlik space. We suppose that this function g satisfies so-called spec u growth condition, where the argument u is bigger or equals than v, and v is bigger than 0, and the exponents p and q have to satisfy this inequality. We also suppose that the non-logarithmic Zhikov's condition holds true. I'll tell a little bit later about logarithmic Zhikov condition and non-logarithmic Zhikov condition on the next slide, but now I'll just present this condition. We denote this condition by G mu, and this condition connects the meaning of the function G in two different points, which differ only on the first argument, where the points x and y belong to the wall with the radius r and with the center x0. And we can see on the right hand side some constants c which depend from the supremum of the function u over the omega is the set where we consider our problem. And we also can see on the right hand side some function mu which depends from the radius, and we suppose that this function satisfies the following condition, that the integral in the point 0 is divergent. And this is the example of the function mu which satisfies this condition. And of course, we suppose that the radius is less than argument v, and v is less or equal than supremum.
Mariia, could you please explain which functions are fixed and which are unknown? So function u of x is, you have to find u of x or g.
Function in this inequality, function g is, for example, if we consider equation, for example, if we consider not equation in not general form, we consider equation, for example, P of X Laplace equation, or for example, this double phase elliptic equation. So function g is equal this gradient in the power P of X minus 2. So it's a concrete function g. Function mu is in this case, it's we need to find this function, or we can suppose that this function exists, and this function has to satisfy some condition.
And function u in this inequality, is this the same function and in the first line?
A function u is the solution of this equation.
So we want to solve this equation, divergence of g times.
No, we don't want to solve this equation. We want to research some qualitative properties of this equation, and we suppose that the function g satisfies this condition.
Mm-hmm. Okay.
Because we need to have some condition on this function.
Thanks.
Okay. And on the next slide, we can see a few examples of this equation. If we can choose function g in many ways, but I'll present only a few examples. The first example is the P of X Laplace equation. It looks like it's the usual P Laplace equation, but here we can see not constants. We can see here function. The second example is the double phase elliptic equation, because we have here two parts, P Laplace equation and Q Laplace equation. And we also can call it's like elliptic equation with peg u growth or peg u phase Laplace equation. And the exponents P and Q have to satisfy this inequality. For example, if Q is less than 2, is so-called singular case. If P is greater than 2, is so-called degenerate case. But it's interesting to consider the case of the exponents P and Q separated by 2. And the coefficient A of X change the phase of equation. For example, if A of X is equal 0, so we have a P Laplace equation. If the function A of X is greater than 0, so the main role plays Q Laplace equation. And the third example is the degenerate double phase elliptic equation. We can see here coefficient A of X. If this coefficient is equal 0, so we have a usual P Laplace equation. We can see a constant P. And if A of X is greater than 0, so we have P Laplace equation with this multiplier. It's only a few examples of our equation, and these equations have a lot of applications. For example, they can be used for mathematical modeling of electrological fluid, which properties significantly change under action of electromagnetic field or temperature. Also, this equation can be used for describing some filters of image processing, but in spite of a lot of applications, our research has a theoretical character. We will investigate quality properties like Harnack inequality and continuity of solution. So now a few words about the history of the problem. Let's consider the P of X Laplace equation. The intensive study of this equation was began in 1980 by Zhikov. Zhikov considered some variational problem with non-standard integrand. And this equation was like an Euler equation for variational problem. And Zhikov considered this equation in context of Lavrentiev phenomenon, because the variability of the exponent leads to appearance Lavrentiev phenomenon, which associated with the different values of solutions to the problem of the minimizing of functional if we take infinitum over the smooth function or function with generalized derivatives. If we can formulate this problem in language of equation, it means that the solution of the corresponding boundary value problem is not unique. And so it's interesting to find condition when the Lagrangian effect is impossible. So this question can be formulated like a question about density of smooth function in the variable exponent Sobolev space. And Zhikov obtained such type of condition, which we called logarithmic Zhikov condition, namely that the function p of x, the oscillation of the function p of x over the ball has to satisfy this inequality. We can see here positive constant L over the logarithm. And if this condition holds, it means that it implies the density of smooth function in the Sobolev spaces. And it means that some regularity properties for equation with standard coercitivity and growth conditions will be held.
Excuse me, am I right that this condition must hold for any x0 from our domain?
Yeah.
Okay.
And this equation under logarithmic condition was investigated by many scientists, and regularity, Harnack inequality, boundary continuity were obtained by Acer, Diffus, Kalkutov, and so on. And if we rewrite this condition in general case in terms of the function g, so we obtain this condition, which have a very close look for the condition on the first slide. The uniqueness difference that on the right hand side we can't find the function mu, because here is logarithmic condition. On the first slide we saw non-logarithmic. For the double phase elliptic equation, the logarithmic condition has the following ways: that the oscillation of the function a of x over the ball has to satisfy this inequality. And for the degenerate double phase elliptic equation, the logarithmic condition has the analogical form. I leave here only one article, but these equations were obtained by many scientists, as it's now it's very popular equations, and many, for example, we have a few scientific group which are very close to our issue. It's scientists from Italy, from Finland, and from Poland. They have a very close issue to us, and especially this scientist Baroni, Colombo, Mingioni. And if we write this logarithmic condition in general form, so we obtain this inequality, like on the previous slide. Then for this equation, for the p of x Laplace equation, Zhikov introduced the following condition, non-logarithmic Zhikov condition. This condition has the following way: that the oscillation of the function p of x over the ball is less or equal than this expression. And here we can see not constant L, we can see here logarithm from the function mu. And the right hand side of the inequality has to tend to 0 when radius tends to 0. And the function mu has to satisfy this inequality, that the integral at the point 0 is equal infinity.
Excuse me, there are such a question. Why we cannot formulate such kind of conditions only considering a model of continuity of this function p, because it is very close, as I think. Or you want to have different condition in different points, but it seems to me that it depends on the radius of the ball. So why this condition is formulated in such a way, but not in the way that, for example, model of continuity of the function p depending on r in such a way that it is integrable with something.
So it's an interesting question. I have never thought about either, because I just thought in the original article and always see only this condition. I need to think about it.
Okay, thank you.
And under here we can see the example of the function mu. It can be a logarithm in power L, where L satisfies this inequality. And Zhikov obtained the density of smooth function in variable exponent Sobolev spaces. And this condition is precise because if L is greater than P over N, the result fails. Also under this
Also, excuse me for interruption, because for me it's slightly a new domain, a new field. What is this Sobolev space? P is now a power like derivative, yes, but it changed. You use the Sobolev space W1 P of X. What is the definition of the Sobolev space?
It's the function which have the one generalized derivative, and the integral.
Probably LP, where P is a variable, right?
Yeah.
Yes, it was my question. I suppose that we have this derivative in power P of X, maybe something, yeah?
Yeah.
Okay.
And later, Pastukhov and Zhikov obtained getting lemma.
I'm sorry. Just I remember I was about to referee some paper, and the comment was that Zhikov was probably the first who one of the first guys who introduced such spaces where LP, where P is variable. So when you integrate some function, say G, modulus of G to the power P of X dx. Somehow they're very useful in some special domains. Sorry.
Okay, let's see. Thank you.
Yeah, he defined two spaces in this article, but I can't remember exactly. He has some space W and another definition for another spaces. I just didn't see this article recently. And so the another result, another result is getting lemma, which was obtained by Pastukhova and Zhikov. It's a lemma about high integrability. Okay, and in a general case, a non-logarithmic Zhikov condition transforms into this inequality. Like on the first slide, we can see here on the right hand side function mu. And the first attempt in this direction to obtain some results under non-logarithmic Zhikov condition were made by Alkhutov and Krashenikova. They obtained the C-log result for the P of X Laplace equation, and he obtained that he improved previous result of Zhikov, because here mu of R is equal double logarithm. Because in the previous slide we can see only one logarithm. And here we can see the condition of the function mu. We will call this condition exponential condition because we can see here exponential. And also under the same exponential condition, Sarnachov, Alfutov, and Sarnachov obtained Harnack's inequality and continuity up to the boundary. For the double phase elliptic equation and the degenerate double phase elliptic equation, under exponential condition, interior continuity up to the boundary and Harnack inequality were obtained by the group of scientists from our institute. And we can see here that this is non-logarithmic Zhikov condition for the double phase elliptic equation and for the degenerate double phase elliptic equation. In our case, we also use double logarithm and we have exponential condition. And now we want to go away from the exponential condition and to obtain a better condition. So in this way, we met a few difficulties. The first difficulties appears if we use the Georgian method in the same realm of the expansion of the positivity. If we have positive solution U and some constant, positive constant N and some positive little constant alpha, and we have the information on the measure, so we will inevitably arrive at the lower bound of the solution. And from this, we can obtain only the exponential condition. So in this case, we can't use the method like the Georgian method, like in the monograph of Ladizhinskaya Uraltsev. If we will use Moser method, in this case, Banstadar calculation, we can obtain a good estimate for the maximum, but on the step when we want to connect the positive and negative exponent, we cannot use the Young-Nirenberg lemma, and instead we can use Strudin's ideas, but in this case, we also obtain the estimate from which we can obtain only exponential condition. So we can't use the Georgian method, the Moser method, and we need to use something new. And the first step in this direction is a generalization of the Georgia-Ladizhinskaya-Uraltseva classes. So if our solution belongs to the spatial W11 this intersection L infinity, and we use the following notation for the any ball from the set omega, and for the any real number k and L, and for the any epsilon, we use the standard notation from the Ladizhinskaya. M minus is a supremum of the expression U minus L minus, supremum over the ball, and U minus L minus here, it's a maximum between two expressions L minus U and 0. And this is our truncate function. And so if we use integral identity for our equation, we use Kuchia-Polly type inequality, Young inequality, and use this function, we can obtain such type inequality. And this inequality we use for the definition of the class of the Georgia-Ladizhinskaya-Uraltseva class. And we can see here that the function g doesn't depend from the nabla u. It depends only from the maximum. So in this case, we don't use Orlik space, and we go away from this space, and it's Orlik space we don't need at all use. And we have the same definition for the Georgia-Maldizinska-Uralska classes for the M plus. So it's a standard classical thing from the monograph. And the advantage of such classes is that I repeat, we move away from all X spaces and we don't need any special properties of these spaces. And moreover, if, for example, we consider the logarithmic case, so in this case, the Holder continuity and Harnack's inequality is the sequel consequences of the definition of class, but it's only for the logarithmic case, not for the non-logarithmic. And the second step in the direction to go away from the exponential condition is to replace the non-logarithmic Zhikov condition by a little.
Excuse me, can you go back to the definition of this class? So you're asking about this maxima and minima for any ball and just to have this condition for all balls. So then you say that you don't need that it is in ordered space. It's we just have a condition at every ball. Can you give some example of such functions which satisfy this condition? How do you check actually this condition?
Check what condition? This inequality?
Yes. How do you check that your function belongs to this class?
Because we use integral identity. We use like a test function, this M minus multiple by truncate function zeta, use integral identity, Kochilin-Poly type inequality, Young's inequality, and we obtain this inequality.
And zeta is some arbitrary function.
Yes, like
Like test
function.
So, and then I just thinking about some non-trivial examples of such function as you consider, because at least in case of Sobolev space with changing parameter power, in case of Orlish space, we can have an examples of such functions. But now you say that you don't need these conditions. So maybe I can reformulate my question. How your classes are related to the previous one? Is it bigger or not?
Classes is the Georgia-Maldizinska classes.
Exactly. Yes. How it is related to the previous spaces?
Previous spaces.
Where this Zhikov logarithmic condition holds.
Maybe was the classes functions for which logarithmic condition holds.
Mm-hmm.
For the class, you mean for the class, for the function u for which this condition holds?
You say that your function u must satisfy some condition. Before this, you have this condition on coefficient j and also on the oscillation of u, and say that if u belongs to some Sobolev space, it holds. Yes.
Mm-hmm.
So my question is, what is about your classes now? Is it true that it's the function from your classes satisfy previous condition, or your classes is wider than? So what can be non-trivial examples of the function from your classes?
Example of concrete function u.
Yes, yes.
No, example of the function u, we haven't example because first of all, we can't to solve our equation in the явном виде.
In precise form, but I'm not asking about the formula for function u. It will be very nice to just to have see such equation has a solution, or even if u is the solution to such equation, it is in our class, but it is not in the logarithmic Zhikov.
No, I can't to say right now example of function which belong to the class Ladyshenskoye-Uralskoye, but don't satisfy logarithmic condition. I don't know example. We just to make like in the general way. I have example, but I have another example for another case for the conditions and G mu, G lambda, but for this case I can't.
Okay. Let's wait for your example. Okay, let's go for that.
And so we propose to replace the non-logarithmic Zhikov condition by another condition. We remove on the right-hand side function mu, but in this inequality we can see some function lambda. On the right-hand side, it's a little function which has to satisfy technically condition. And for example, this function logarithmic 1 over r in power minus gamma satisfy this condition. And also I can conclude once more that the direct application of Moses for the Georgian method leads us to the exponent condition. So we use a workaround which goes back to the old Landis ideas and his so-called growth type lemma. We construct the auxiliary solutions of potential type and obtain lower and upper bounds of auxiliary solutions. And now I'll present a few examples. How can we go from the G mu condition to the condition G lambda, and what is the connection between function lambda and mu? For example, if we have a double phase elliptic equation, it means that the function G is equal this expression, and we have a G mu condition. Then if we want to go to the G lambda condition, we need to find the difference between the meaning of the function G in two different points, which differ only on the first argument. Then we use this notation and obtain this expression. Then we use that the argument has to be less or equal than gamma multiplied by lambda. And we obtain this expression. We need that on the right hand side the function lambda and mu will be absent. So in this case we suppose that the lambda is equal 1 over mu, and then we obtain that on the right hand side we have only constants, and this multiplier we estimate by G. And we obtain, if we these terms goes to the right hand side, so we obtain G lambda condition, and this is a connection between lambda and mu. And like example, if we take mu is equal logarithm power b beta, so lambda is equal this expression, and in this case exponential condition fails. It means that this integral will be finite. And in the same way we can obtain for the generate double phase equation, we have also, for example, if mu is equal double logarithm, lambda is equal logarithm power minus beta, in this case exponential condition also will be failed. And the same for the degenerate double phase elliptic equation in case when we have here two multipliers. And now I can formulate the main results. Under the GMU condition, we obtain analog of the local clustering lemma, obtain weak Harnack inequality, obtain Harnack inequality. Under the G lambda condition, we obtain local clustering lemma and weak Harnack inequality. And under the G lambda and G mu conditions, we obtained Harnack inequality. Okay, it's all.
Can you go back to this main results, please? To the previous one. Okay. Okay, so let us at least we can see it.
It's a very big formulas. It's very difficult for understanding because it's very narrow issue.
No problem. No problem. So you have the after this local clustering, you get the integrability of solution in some power and estimation to this. Then, but in the title of the talk, you announced also continuity at the boundary, yeah?
Yes, sorry, I forget about that. Under the G lambda condition, we obtain the continuity of solution. Sorry.
Yes, it's reasonable that it follows from Harnack inequality, but what you said is that continuity is the boundary.
No, only continuity.
Only continuity.
Continuity to the boundary were obtained by Igor Skripnik and Vaitovich and Hadji. I didn't present here their result.
I see.
But it's I can say that it's a new issue for me because I have another issue when I was a PhD, and it was a removability result for anisotropic forms media equation. It was also a very narrow issue, and then after my PhD, I changed the issue, and it's very difficult for me, but I'm trying to figure out. But maybe for the program, this equation is not appropriate. You asked me about anisotropic equation, but I'm trying to continue my work with anisotropic equation, but it's this direction I continue alone without my supervisor, so it's not so easy for me. But the previous topic is removability result. It's like a classical result, but it has not a practical meaning. It's just you obtain a removability result, and you even can't to use this for another theory or something. Also, it's like not so popular.
Oh, thank you. Thank you very much for, I think, the introduction to this theory. Maybe somebody have questions or comments, please. Okay, thank you again. And this really useful inequalities which you get in the end, which you present. And I think that it was interesting for all participants of the seminar. So thank you very much.
Thank you for the question. It's very useful for me to see, because I see only one direction from the technically, maybe only technically, how to use technique to figure out with method. But after the seminar, I always try to use the question which were asked for me, because it's very interesting to see from another side, to find some example, because I even have never thought about a thing that you asked me.
Okay. Georgi, maybe you know who will be the next speaker?
The next speaker will be Andrei Pilipenko.
Okay. So for this session, we ended our work. Thank everybody, and bye. Up to the next week. Bye.
Bye.
Have a good day. Bye.
Good day.